So in this video, we will be seeing the transducer engineering in the topic of other transducers. In that specifically piezoelectric transducer and Hall effect transducer. So we all have been studying the basics of piezoelectric transducer in the second semesters of our measurement subjects. So a piezoelectric material is one in which an electric potential appears across the surface of a crystal if the dimension of the crystal are changed by the application of a mechanical force. So the surface of the piezoelectric material will change its dimension on applying the mechanical force on it, which causes the electric potential across the terminals. So the voltage is produced due to the displacement of charge. When the force is applied, the dimension is changed due to the displacement. So the displacement of charge occurs, which causes the potential difference. So this effect is reversible. So by varying the voltage to the proper axis of the crystal, it will change the dimension of the crystal, thereby deforming it. So it is an reversible process. This phenomena is known as piezoelectric effect. This is the piezo setup of your piezoelectric transducer. You have a membrane, so the pressure is given through the pressure knob. So your crystal is here. So when the membrane compresses by the pressure, the crystal deforms itself, and the output voltage occurs due to the variation in the electric charge. So when you are giving an input supply in the reverse condition, the crystal deforms it to its original structure. Okay. So the materials that can be used for piezoelectric transducers are rostelled salt, ammonium dihydrogen phosphate, quartz, ceramics made with barium titanate, dipotassium tetrate, potassium hydroxide phosphate, and lithium sulfate. We will be mostly using rostelled salt for the piezoelectric transducers. There are four modes of operation of your piezoelectric material, that is thickness expansion. The thickness will be expanded or transverse. The opposite ends will be expanded, or thickness shear or phase shear. The mode of motion employed depends on the shape of the body relative to the crystal axis and the location of the electrode. So how the shape changes depends upon the electrode position and the axis of the crystal where it is placed. The piezoelectric element used for converting mechanical motion into electrical signal may be thought as charge generator. So mechanical to electric signal, it is converted as charge generator, right? So mechanical deformation generates a charge. So by mechanically deforming your crystal, a charge is generated, and this charge appears across the voltage across the electrode. So the output voltage E naught or V naught is given as charge divided by your C. Okay, so it's direction sensitive. Depending upon the direction, the output voltage changes to positive, negative, or negative to positive. So a crystal is placed between a solid base and a force summing membrane, as I shown in the first slide. So the crystal is placed between the solid base and the force membrane, and an external force is applied, entering the transducer through its pressure port, applies pressure at the top. This produces an EMF across the voltage proportional to the magnitude of applied force. Depending upon the amount of force or pressure or magnitude of the pressure, the crystal deforms and an EMF is produced. The magnitude and polarity of the induced EMF charges are proportional to the magnitude and direction of applied force. So based on the magnitude and direction of your force, the magnitude and polarity of induced charge depends. So Q is equal to force into distance. So D is nothing but your crystal charge sensitivity, which is nothing but C by N constant for given crystal. So based on a crystal material. F is the force given or pressure given in Newton. So the picture resembles your for various four modes of operation of your piezoelectric crystals. So the first one is by the thickness of the crystal is deformed, whereas here the face is deformed, and here the thickness expanded. Shear means it will be shrinking, right? So that is nothing but thickness here. Here it is expanded and transverse expansion. So equivalent circuit of a piezoelectric transducer. The source is a charge generator. As we have seen already, the source is a charge generator. The value of Q is equal to dF. That is how much pressure you are giving, the charge value will be different. So the charge generated is across the capacitance Cp of the crystal and its leakage resistance. Across your resistance and capacitance, you will be getting your voltage. Okay. So the advantages of piezoelectric crystals or transducers are its size is small, and it is the weight of the crystal is less, and it is rugged in construction. It is a self-generating type because we are only giving a pressure, right? No external power is used, and the outputs are quite large and have a good frequency response. Whereas the disadvantage is the output voltage is affected by temperature variation of the crystal. If the based on the temperature, the output voltage varies. So for dynamic measurements only it can be used, not for static measurements. So the application of it is applied in the measurement of force or pressure or temperature and high frequency accelerometers. And moving to our Hall effect transducer, it is one that varies its output voltage in response to the magnetic field, whereas piezoelectric transducer respond to the change in pressure. Here it respond to the change in magnetic field. Hall effect sensors are used for proximity switching, positioning, speed detection, and current sensing application. In Hall effect sensor, a thin strip of metal has current. Through a thin strip of metal, the current is applied. In the presence of magnetic field, the electrons are deflected towards the edge of the metal strip, producing a voltage gradient or change in voltage. Simplest form, the sensor operates as an analog transducer, directly turning a voltage. So with a known magnetic field, the distance from the Hall plate can be measured using the relative position of your magnet can be deduced. So working principle, when a beam of electric charge passes through the magnetic field, force acts on the particle and the beam is deflected from the straight path. The flow of electron crosses a beam of charged carriers. When the conductor is placed in the magnetic field perpendicular to the direction of the electron, then it is deflected from the straight path, thereby creating the voltage difference between the two planes, which is said to be as Hall voltage. So the materials used in Hall effects are gallium arsenide, indium phosphate, indium antimonide, and graphene. Mostly gallium arsenide is used. This is the pictorial representation of your Hall effect sensor. So here will be a constant current flow. When the magnet comes, the potential difference between the two across the two ends of the plate is taken as Hall voltage. So application, position sensing, direct current transformer, automotive fuel level indicator, and keyboard switch. So the advantages are operate as an electronic switch. It can be operated as an electronic switch. Cost is less, then more reliable. Up to 100 kilohertz it can be offered. So not suffer from contact bounce or hysteresis losses, and also not easily affected by the environmental contaminations like heat, etc. Can measure a wide range of magnetic fields. Whereas the disadvantages is lower measuring accuracy than magnetometers, difficulty in operating under strong external magnetic field, low output drive capabilities, and an amplifier, voltage regulator, and output transistor is required to have become a practical unit. Thank you.